Now, Magnetism, Lesson 2, Theory. Now, 1 second, let me close that window. Now, look at it. First, let us visualize what is a magnetic field. And the symbol for magnetic field is B. It is a vector quantity. In previous lessons, we have learnt about how a current carrying wire was behaving as a magnet, whole thing as a magnet. And if you have a magnet, also piece of bar magnet, north, south here, all around it, this side, this side, this side, this side, above it, below it. Similarly, for this wire carrying current, on this side, on this side, on this side, on this side, above it, below it, all around it, all around this, that is in space. Up to certain extent, its effect is felt. Its effect is felt means if you keep pieces of iron, small pieces of iron here or here or here or here or here or below it, anywhere around it, that is up to certain extent, that is certain extent around it, it can attract. So that region of space, all around it, within which its magnetic effect is felt, is called its magnetic field. So that is what I am saying. The space, not plane, the space around a magnet, or the space around a current carrying wire, because a current carrying wire also behaves as a magnet. So all around it, in which the magnetic effect is felt. How the magnetic effect is felt? Either you keep another magnet that will be influenced by it, that will be influenced by this wire carrying conductor, or will be influenced by the magnet. And that is what, that space all around it is called its magnetic field. Here, suppose if you keep a piece of iron here, that is attracted. But if you keep it here, suppose it is not attracted. Therefore, this is not within its magnetic field. It is outside its magnetic field. So the space around a magnet or a space around a current carrying conductor in which the magnetic effect is felt is called its magnetic field. Then, to visualize this, the concept of magnetic field lines were introduced. So, what are field lines? I will explain you. I will explain you through this diagram. First, let us explain the statement. It is not actually a line. It is an imaginary curve, not a straight line. The tangent to which at any point gives the direction of the magnetic field B at that point. Suppose this line, this is a magnetic field, a field line. This is a magnetic field line. What is the direction of the magnetic field here? To this curve at this point, draw a tangent. So this is the direction of the magnetic field. Whether the field is strong here or not, that depends. If you keep a unit area here, and if you can find out the number of lines of force passing through that normally, more the number of lines of force passing through that normally, more is the strength of the magnetic field. So now let us explain this, how to draw magnetic field lines. Then I will come back to the properties of magnetic field lines. Now for that, what I have done is, what do you do? On a piece of paper, you take a bar magnet, north-south, keep it on it. Now, these circular ones, look, this one, this one, this one, this one, this one, all these circular ones, each one is a small magnetic compass. It has a magnetic needle in it. This is the magnetic needle, 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 which is capable of rotating in a horizontal plane, either like this or like this. Why it will rotate? The moment you keep it anywhere, that needle will experience a torque, so it will be rotating due to the torque, and will align itself at a particular position for a given place. For example, if that compass needle is, if you have a compass that you are keeping it here, this is the point about which this needle is capable of rotating. North pole, south pole. If you keep this compass here, the needle will point this way. The red portion is the north. If you keep the compass here, the needle will point this way, this way. This red is the north. If you keep the compass here, the needle will point this way. If you keep the compass here, little small compass, the magnetic needle inside it will point this way. If you keep it here, exactly at the midpoint, it will be like this. If you keep it here, it will point like this. If you keep it here, point like this. If you keep it here, it will point like this. If you keep it here, it will point like this. This red part that I have shown is the north pole of the compass needle, magnetic needle. Similarly, I have drawn it here. Now, so if you with a free hand, if you join this point, 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 you get a line like this. Right? This is called a magnetic line of force due to this bar magnet. Similarly here, they start from the north pole of the bar magnet, and they don't finish at the south pole. They are actually all the lines of force are passing through this magnet, right? So these are your magnetic lines of force. That is how you draw it for a bar magnet. If you keep the compass at this position, 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 it will be like this. Similarly, if you keep at this position, this position, this position, this position, this position, this position, so on, then it will be like this. So that is how you draw the magnetic lines of force. So once you know how to draw magnetic lines of force, if I ask you what is the direction of the field here, draw a tangent. What is the direction of the field here? Draw a tangent, right? So that is how the direction, how you draw the magnetic lines of force for a bar magnet. Now let us come to find out its properties. Now all these lines of force are closed continuous loop. Closed means they begin with the north pole. They don't end at the south pole. They are passing through the magnet. Therefore, they are continuous loops. These are all continuous loops. This is also a continuous loop. So they are all closed continuous loops. Outside the body of the magnet, the direction of the magnetic field lines is from north pole of the bar magnet to the south pole, outside. Inside, it is from south to north, inside the magnet. A tangent to the field line at any point on the line gives the direction of the magnetic field at that point. Now, what is the magnitude of that magnetic field at any point? The magnitude of the magnetic field at any point is represented by the number of magnetic field lines passing normally through unit area held at that point. Means, if you want to find out the magnitude of the magnetic field here, hold a unit area here and see how many lines of force are passing through this normally. Let us say it is 50. If you hold it here, if you want to find the strength of the magnetic field, magnitude of the magnetic field, hold a unit area here and see how many lines of force are passing through this normally. If it is 50 here, it will not be 50 here, it will be less than that. Means the strength of the magnetic field is more here, is less here. Now, so that is what I said. The magnitude of B at any point is represented by the number of magnetic field lines passing normally through unit area at that point. That is same thing as saying wherever the flux is more, the magnitude of the magnetic field is more. Then no two magnetic field lines intersect each other. Means it is never like this. One field is like this, the other is like this. If it is so, you at this point you can draw a tangent to this line, and at this point you can draw a tangent to this line also, which means at this point the field is in two different directions, which is not possible, because here if you keep a compass needle, it will point only in one direction, either in this direction or in this direction. That is same thing as saying it has a unique direction at a given point, not two different directions. Now, then coming back to your sixth property, magnetic field lines have a tendency to contract longitudinally, means the lengthwise they try to shorten the length. That is same thing as saying two unlike poles, that is a north pole and a south pole, they attract each other. You can imagine from here, let us consider this line of force. This has a tendency to decrease its length. That is same thing as saying a north and south, they attract each other. So that is the tendency. And similarly, magnetic field lines have a tendency to dilate laterally, sidewise. Sidewise means this is trying to push to this way, this is trying to push to this way. That is same thing as saying two similar poles, they repel each other. South repel, north repel. Like poles repel each other. Then from this point onwards, we'll move on to derivations, different kinds of derivations in magnetism. So first let us begin with magnetic dipole. What is a magnetic dipole, and what is a dipole moment, and what is its direction? Here I have shown you a magnet, a bar magnet, north pole, south pole. Let the distance between the south and north is taken as L. You can take it as L also, you can take it as X also. And the pole strength of this as well as this, suppose they are equal, and they have to be equal, let it be M. 2L is a vector quantity pointing from south to north to this side. 2L, called the magnetic length pointing from south to north of the bar magnet. M is the pole strength of each pole. Then a quantity called M, capital M, defined as pole strength and its product with 2L. Look, I'm using the word product, not multiplication, because this is not a number, this is not a number. You can only multiply numbers. 5 into 4 is 20, but you cannot say 5 into something, a length. The word multiplication is used for numbers. Numbers are multiplied. This is not a number, this is not a number. Although their magnitudes are expressed in number, but it is not a number, this is not a number. Their magnitudes will be expressed in number. A quantity represented as capital M is the product of the pole strength and the length, the magnetic length of the magnet. This thing is called the magnetic moment of a magnetic dipole. There are two poles, therefore it is called a dipole, and its direction is from south to north. Similar thing we had studied in electrostatics. Minus Q plus Q, two equal and opposite charges separated by a distance 2a was called an electric dipole, and a quantity called P, which was equal to 2aq, was called the electric dipole moment. It was directed from minus Q to plus Q. It was a vector quantity. Similarly here in magnetism, the magnetic dipole moment capital M is the product of the pole strength into the magnetic length, and it is directed from south to north, and its unit is joule per Tesla, or same thing as ampere meter square. From next lesson we'll move on to finding different derivations, that is how to find the magnetic field due to a bar magnet on the axial line here. And we'll find out due to a bar magnet means magnetic dipole, what is the strength of the magnetic field on the equatorial line here. Here at a distance r from here at a distance r from here. In the next lesson, we'll find out the magnetic field due to this dipole on the axial line here, and also due to this on the equatorial line here. And the derivations will be almost similar, similar to that we did in electrostatics.